Welcome everybody to another N3AS seminar. Today we're very pleased to be joined by Jeff Dror from UC Santa Cruz, who's going to tell us about new insights into axion-lepton interactions. So please, Jeff, take it away.
Thanks, Evan, and thanks to everybody for having me for the seminar. It's really an honor to get to talk to everybody here. I'd love to have chatting afterwards, but also feel free to ask questions during if there's anything that's unclear or otherwise. So I'll tell you about some work that I've done in collaboration with people here at UC Santa Cruz by Wolfgang Altmanschaffer and Stefania Gori, and it just came out a few weeks ago, so I'm very excited about it. And the idea, as the title suggests, is just trying to understand what happens when you interact an axion with leptons. And it's obviously a very old idea, but there's surprisingly some new insights that we were able to gather by studying this more recently. So here's the outline of what I want to talk about today. I want to start with giving you an introduction towards lepton-axion interactions generally. And really the high point of my talk, if you wish, will be the second part here, which will be reformulating the usual Lagrangian that we discussed in this context in a way that's going to make a few very interesting results manifest. So I'll go over how that works. And the new intuitions that we gain through this reformulation will tell us about some new opportunities to look for axions, and I'll discuss what those are. And finally, if I have time, which I may not, will be to try to talk about how these new detection strategies and new constraints that I'll derive for you have implications on existing models in the literature. So that I want to start with this notion of an axion interacting with leptons. And I should mention for those in the audience that use this word a little bit more in a different way than I do, I use an axion in a very general way, just some sort of shift symmetric particle, meaning that the interactions that I want to study are going to be derivatively coupled for the axion here to some sort of current J mu, PQ here standing for PQ symmetry. Now, the most general possible J mu or current that you can interact this axion with is shown for you in the center of the screen. You have one term over here, which is a vector coupling to charged leptons L. You have a term which is an axial vector coupling to charged leptons, and a neutrino coupling here on the right-hand side. Something which is a little bit awkward for people that think about axions is I prefer to normalize this current, this J mu here, to the mass of the charged lepton that I'm interacting with. And the reason I like to do this is because it makes the couplings that are actually physical manifest. There's only 3 parameters that are physical inside this theory, and I'm highlighting them. This is just a convenient normalization that I can choose how I please. And this will become a little bit useful, as you'll see later on when I show you constraints. Now, there's a lot of funny claims in the literature when trying to kind of peruse to understand the constraints on this Lagrangian. And I'm going to kind of discuss the nuances of those different claims and a little bit about how, in which conditions they really are valid or invalid. One claim you often hear is that this first term over here, this vector coupling, is just unphysical. You can forget about it entirely. Another claim that you often hear is that the neutrino coupling out here on the right-hand side is proportional to the neutrino masses. And finally, you often see people discussing about how this interaction over here, the middle one in your screen, here written in terms of electrons, is just given by this Yukawa term form over here. So you can replace this interaction with this term over here. And these 3 claims have a lot of truth to them, but they also have subtleties that make them different in certain cases. And I want to discuss what those are. So here's the Lagrangian that I just showed you on the top of your screen. You're just seeing it one more time. And the first question that I want to ask here is, well, should I demand electroweak invariance onto this Lagrangian? I have 3 couplings, 2 leptons and neutrinos, and I've not in any way related these 3 couplings thus far. But maybe you should say that I should demand perhaps that this coupling minus this coupling should be equal to the neutrino coupling because of the fact that the left-handed electron is related to the left-handed or the neutrino in that doublet. So the first approach you might take is obviously just yes, you should demand it because we observe electroweak symmetry is a very good symmetry. And the argument here is that you should probably impose electroweak symmetry on the charges of the global symmetry that this axion particle interacts with. That's kind of the technical answer, if you wish. What happens then is you reduce the number of parameters inside this theory from 3 into just 2 parameters. And a useful benchmark model that you could see in the literature many times is that you interact only only a charged lepton here, and you put a projector, a right-handed projector, meaning that you're only interacting with the right-handed electron. And I'm going to address this model as we go along. So this will be my benchmark or my poster boy, if you wish, for this case, where you impose electroweak symmetry onto the Lagrangian. The other answer is, of course, no. And the reason why this might seem like the right approach is because a breaking of electroweak invariance, first of all, is even generated by RG running. Below the electroweak scale, the photon only couples to electrons, not neutrinos. So any sort of RG running breaks this relationship that might have existed in the UV and will change these relationships. So you can then, with that in mind, consider these 3 as totally independent couplings. If that answer is not good enough for you, you also have breaking potentially by higher dimensional operators like this one over here. This one, if you stare at this long enough, you can convince yourself this would only be a coupling to the left-handed electron and not the neutrino. So it does satisfy this electroweak breaking condition. So it would be under this umbrella over here. The benchmark model that I want to tackle is one that you see sprinkled around the literature. And that's where you have just a gamma 5 sitting inside here. So I'm going to come back to this model where you have only a gamma 5, and to this model where you have a full right-handed projector. Now, if you've thought about light scalars before, you've probably heard some terms in the literature like the Myron, the DFSZ axion, the KSVZ axion. These different cases have the DFSZ axion is kind of primarily of this form over here, where it's electroweak invariant. The KSVZ is primarily of the electroweak violating way. And the Myron is kind of something else entirely. It's really electroweak symmetric, but it's not of the form that I showed over here. Now, the critical point and why I'm kind of harping on this right away is that whether or not you require electroweak symmetry on this Lagrangian ends up having dramatic consequences in how you want to look for these light particles. Now, the Lagrangian that I just showed you, it was d mu A acting on multiplied by a current, J mu. You can integrate by parts as you please and ask the question, well, what does this d mu J mu look like if you write it down? And this is going to be a very convenient form because it's going to reveal really physically what's interesting about these different terms and when you want to study which case. There's a few different terms that show up with this divergence of the current here. And the first term is this Yukawa-like term. You have a coupling out front, L bar gamma 5 L. This is, if you wish, the standard form that you often see in literature when discussed in this context. You could produce an axion by just interacting with electrons, as shown here. Now, this has driven most of the phenomenology in the axion literature, and I want to show you a little bit what the constraints are in this parameter space. So here I'm focusing on the electron coupling. That's the vertical axis, GEE. This is the axial vector coupling, to be more specific, of the axion to charged electrons. And on the horizontal axis, I have here the mass of this axion. And here are all the different efforts people have put together to try to study this parameter space, and they're shown here in gray. At the highest case here, you have, at the highest masses, you have collider constraints. A little bit lower masses, you have G-2, which carries some caveats that we can discuss if people are interested. And then you have the various different beamed up experiments that were taking place quite a few years ago now on the left-hand side. And you also see some supernova constraints on the bottom of your screen. Now, if you continue and write down the other terms that are present when taking the divergence of this current, the next term you start to find are what are I could like to call anomaly terms. What they are is a coupling to the field strength tensor of the W boson here, W plus W tilde minus, and then some sort of funny coefficient. You have 1 over 4 pi squared that shows up because this is really a loop effect, if you wish, not a tree level effect like the previous case. But the critical feature of these anomaly terms is that they have a 1 over the mass of the charged lepton that shows up here. In other words, unlike for the case of the standard form, where the 1 over the mass of the charged lepton goes swallowed up by integration by parts, that does not happen for this term. And that's going to make these sort of terms very important when trying to study the constraints on this theory. Now, you can go ahead and superimpose constraints here for one case, one of the benchmark models that I mentioned earlier, the weak violating case in this case. And here are the various different efforts people put together to try to look for these types of models. This is a k-on decaying to pi a, beta k star, and k long to pi naught a. So they really are substantially improving over different collider constraints. And really that's coming from the fact that there's a 1 over the mass of the charged lepton appearing in the denominator. Now there's a final term which has basically gotten little to no attention in the literature, and that's really the highlight of this talk. And that's the term shown on the bottom of your screen. You don't have the loop suppression like we had for the previous term, but you still have a coupling to the W boson here with a charged lepton and a neutrino. And really what happens is the effect on the right-hand side, where you have this funny little 4-point interaction that's showing up. But the critical feature that you might already be observing is that the mass of the charged lepton here is still present in the denominator, which means that, again, this is going to be a very important process to try to study if this term is there. Now, there's different combinations for these couplings and different signs, and you might wonder in which cases do different ones go to 0. The middle term, for example, those ones will go to 0 if you have an axion that interacts with differences in leptons as the charges. So if you remember things like L mu minus L tau is a popular thing to gauge in the standard model. If you just have an axion interacting with those sort of charges, you'll remove these anomaly terms. For the second case over here, for this weak vertex, the one that I really want to highlight, this combination here goes to 0 if you don't have any electric violation inside the initial Lagrangian. So it's that particular combination that makes this term not important. Now, the focus that I want to go from now is to first of all point out the importance of this weak vertex and study in which cases it's going to be a dramatic effect in your parameter space. And it turns out, as a corollary of that, I'll have a situation where I can also place a new bound even on the standard vertex. That was a big surprise for us when we started working on this project. Is there any questions? I'm really pause for a moment here. Okay. So with that, we can now go to understanding the detection opportunities for this kind of interaction. And there's 3 different opportunities that I want to discuss. The first one is charged meson decays. This will be relevant for weak violating and weak preserving axions in those 2 cases that I mentioned earlier. Here I'm calling them ALPS, but these terms are interchangeable for my purposes. Another opportunity that I want to discuss are W boson decays. These will be relevant only for the weak violating case. And finally, it turns out that even proton beam dumps, not electron beam dumps, like conventionally studied, are also useful in trying to look for these weak violating axions. And I'm going to focus, as I already kind of have been implicitly, on the electron case of the interactions. You could study this for all sorts of, for the other charged leptons, for the other leptons. But we focused entirely on this case for concreteness. The first case I want to discuss are axions or axion-like particles from pi plus decay. This is an old idea that was already discussed in the beginning of the notion of what an axion even is in these papers over here. But the initial discussions were all about the effect of an axion and pi zero mixing. So the different kind of interaction than the one that I want to discuss, which is an axion interacting with electrons. The first point to emphasize that this is a good channel to try to look for axions, because if you have a 3-body process instead of a 2-body, like what's depicted for you in the center of your screen, you can remove the usual helicity suppression inside pion decays, which means that relatively speaking, the axion is going to be a more enhanced process compared to the usual decay that you might be studying. The first process over here is relying on the standard vertex, this N3AS vertex that I mentioned on the previous slide. But you can also do the same process with the weak vertex, this 4-point interaction that requires weak violation to actually take place. If you focus on the standard vertex, you go ahead and you calculate what is the rate, and you find an answer that scales like GE squared, this coupling squared, times some of the dimensionless ratio. That's the mass of the pion squared, F pi squared, divided by the mass of the W boson. And if you go ahead and compute what is the branching ratio, it turns out you get a number about 10 to the minus 8 for couplings that roughly saturate the collider bounds of about 10 to the minus 3. If instead you go ahead and use this weak vertex, you'll find that you'll have a decay rate which is of the same form as shown above here, but with a new factor. This new factor is m pi over me squared. It's a very, very substantial enhancement. It's about a factor of 10 over 100 squared inside the rate. Now, quantitatively, what you find is the branching ratio looks something like this. For the same sort of couplings that I mentioned above, we're talking about a branching ratio of about 4.5 times 10 to the minus 5. Now, what's really interesting, I think, is that both these numbers here are very detectable numbers. Well, we have many pions. We've looked for very small branching ratios. And these, you can go ahead and constrain this parameter space very well. And that goes to the next slide, which is all about what kind of experiments we have that are capable of looking for this process. In the push that exists right now to try to look for this process was carried out by the Syndrome collaboration. They were a collaboration that was situated out in PSI, a facility in Switzerland, I believe, where they have a huge number of muons and pions, and they looked for light particles that are produced in that decay. Here you see the physicists that carried out this experiment that are hard at work. They are sitting inside their experiment, that you see here, and there's a beam that will be going inside this big magnet here and trying to look for decays of those particles. This was happening all the way back in the 80s, so it's quite an old experiment by my standards. But even still, they were able to reach branching ratios that are about 10 to the minus 10. So just really spectacular measurements that were done over 40 years ago, or about 40 years ago. But the future here is also quite interesting. Right now, there's been a new effort called Pioneer. And the Pioneer experiment is right now in a maturing stage. They are funded, and they're starting to now do some test runs at the same facility that was carried out all the way back in the 80s by the Syndrome collaboration. But right now, they're just going to be using much more modern technology to make a similar type of measurement that was done back here. And the idea is that you shoot some pion beam, you hit a big target. It's called an active target made of argon, I believe. And this active target goes ahead and kicks out these different light particles, and you try to study the different light particles that are being produced inside these decays. Now, I've just been attending this nice workshop that was happening here at UC Santa Cruz, all about trying to make this Pioneer idea a reality and what it takes to push this frontier. It was just happening literally a few days ago. And they're talking about potentially reaching branching ratios of about 10 to the minus 11. If their timing is kind of the minimal requirements, they could potentially reach also 10 to the minus 12, even 10 to the minus 13. The issues here are not the pions themselves. They're going to have many, many pions. The issues are all about timing and trying to differentiate all these different decays. So depending on what capabilities they're able to reach, they will definitely improve upon the Syndrome limit, and how much is kind of what remains to be seen. But I'll be making some projections with this assumption in mind, about 10 to the minus 11 in the branch ratio. And to see how important these two different bounds, the past and the future, are in the parameter space, I want to bring you back to this coupling versus mass space I showed you a couple of slides ago. Here I'm zooming in a little bit on the top part of this space because I'm studying the weak preserving axion. And as you'll see in just one moment, that's really where you want to try to look for is this kind of relatively larger coupling than in the previous case. With all that preparation, here's the bound you get from Syndrome. This is an existing bound in the sense that it was already carried out back by this old collaboration. but no one has yet written out the bound. So this is actually the first time that I have seen this bound in diagrammatic form in this sort of parameter space. I was very surprised that I was able to cover a new space, considering there's been a lot of models that have been sitting up here for various different reasons, for talking about anomalies, for G-2, et cetera, et cetera. So it's really kind of interesting that, in fact, you can still have a very powerful bound that was not yet appreciated in the literature. But in the future, you're going to improve upon that. Here's the 10 to the minus 11 line shown for you in dashed. If you can get 10 to the minus 12, you'll kind of get another factor of a few over this 10 to the minus 11 line. Now, the kind of big effects, if you wish, are going to be in the weak violating axion, because that's where, remember, you have the enhancement inside this process. You can use that weak vertex that I was mentioning. And here you're looking at the projections for what you can do from the syndrome collaborations data. We're talking here about improving over the current bounds by about an order of magnitude in both coupling and in masses. So it's really quite dramatic how powerful these pion decays are for these types of models. And if you go ahead and superimpose here the future bounds, that's what's shown for you in dashed line. Now, you might ask, well, if you can do pions, why not other mesons? And in fact, you can. The kaons being the next example that I want to discuss here. Here, in this case, the k to pi e nu is even smaller than the previous case, relatively speaking. And there have been searches for inclusive processes. We're looking for k plus e nu, e plus e minus. But to my knowledge, there is no bump hunt, which is being done, has been done for this kaon decays. And that's a little bit unfortunate because they're only able to reach branching ratios of about 10 to the minus 8 right now. You could probably significantly improve upon that if you were able to do some sort of bump hunt in these very low invariant masses of the electrons of these final states. But nevertheless, you can now superimpose those constraints on this parameter space. Here you see the results for kaons. The case of about 10 to the minus 8, that current bound is shown here in red for the weak preserving axion. And here you see the future bounds, which are relying here on some sort of kaon factories doing dedicated search for this process. And in the weak violating case, because you win by m meson over m electrons squared, you have a nice boost for your kaon decay rate, and you're able to enter into this kind of parameter space out here. If you go ahead and you move along now and then push this to D, D sub S, B, B sub S, you'll keep winning for the weak violating case because you're getting a better and better enhancement by this m meson squared over m electron squared. But unfortunately, the flavor preserving decays in this case are so significant that in terms of branching ratios, you're not going to win very much. You would have to be reaching branching ratios of these mesons that are at least 10 to the minus 6 to really make an impact here. And that's quite tough for these heavy flavored mesons. So while that might be possible for D sub S, for example, to make a splash, it's not so clear, and there is no present prospects that, or present experiments that have probed this parameter space to the best of my knowledge. Any questions on this case? Okay. The final example that I want to mention is W boson decay. Actually, sorry, two more examples. The next example is W boson decay. And this case, as I briefly mentioned, is only relevant for the weak violating axion. Otherwise, you can, of course, have a W decaying to an axion, neutrino, and electron no matter what, but it's just not going to be a very significant bound just kind of using the standard vertex that I was mentioning earlier. But for a weak violating axion, you get a huge benefit. You win by mw squared over m electron squared. So it's just an outrageous benefit, if you wish, inside the rate. And the branching ratio ends up being of order 1 if you have couplings that are about 10 to the minus 3 or so, kind of saturating the old bounds, if you wish. What's interesting is I've not been able to see any sort of direct searches for rare decays in W boson, or for rare W boson decays into light particles. You can go ahead and open the PDG and look at the various decay modes. And there hasn't been much effort to try to look for W, E, nu, E, E, for example. Of course, the rate is very small in the standard model, but as I've shown you, the rate for an axion-induced process can be much, much larger. It can be even of order 1 if you saturate the kind of current constraints. So that means you can even set a bound by doing something extremely conservative, and that's by just requiring that this new process not contribute so much that it'll go over the error bars on the total width of the W boson. This puts a very conservative branching ratio of the decays of W bosons to E nu axion of about 0.04. With a dedicated search, given how many W bosons we're creating every day at the LHC, we can reach at least about branch ratios about 10 to the minus 5. That's kind of my rough estimate by comparing to other kinds of processes that exist inside the PDG. With that in mind, we can superimpose on this parameter space these two different bounds. The current bound is shown for you in olive. It's not tackling new parameter space right now. But if you go ahead and you try to push a dedicated search for this process, you could really expand your capabilities and push into couplings as low as about the value shown here if you reach about 10 to the minus 5 in the branching ratios. The final case that I want to mention are proton beamed up experiments. The example of this that has been studied a lot in the literature is the CHARM experiment that was occurring back in the 80s and 90s, I believe. And there you have a proton beam that was the same beam that ends up now kind of running through the LHC in a sense. It's a 400 GeV beam, and it gets smashed into, I believe, a copper target that's depicted here by this pink rectangle, and it produces all sorts of a rich collection of different mesons. You get a pi pluses, k pluses, d pluses, d sub s, b pluses here, and all those can travel through your experiment for a short distance until they either decay or get absorbed, or both. And the idea was that those sort of decays can produce light particles as shown here for the axion, and that axion can then go ahead and decay to E plus E minus and be claimed as a detection on the other side of this dump. Now, this has been studied before for flavor changing interactions induced by the axion. So for example, K to pi axion, B to K axion, et cetera, et cetera. This is the first time, as far as I'm aware, that people have studied the possibility of trying to use semi-leptonic decays of these different charged mesons. And that also means that you'll also be using a new collection of mesons that hasn't been discussed in literature before, and that required a little bit of digging into the cross-sections of production for these different mesons, and that's what we carried out. They observed 0 events back in 1985, so that means you can go to the same parameter space and put a constraint, and that's what's shown here for you in yellow. Now, I want to contrast the bound that's here with the bounds that are shown here in gray, and you see here that it's able to go a little bit to the right-hand side, but really it's using a dramatically different source, if you wish. These were electron beamed up experiments using the standard vertex. This is a whole new type of process in a sense, because it's all coming from these rare meson decays that are very enhanced for the weak violating axion. And with that, I want to kind of take my final slide here and go to the implications of the constraints that I just mentioned. And the implications that I want to discuss are not going to be for the weak violating case, where the implications are obviously kind of there. I want to discuss the implications for the weak preserving case. That's it, if you wish, the kind of more classic axion that people have been studying for quite some time. An example of that is this nice paper by Daniela Alves and Neil Weiner back in 2017, and a follow-up by Daniele more recently, where they looked at the possibility that the QCD axion, the one that solves the strong CP problem, could actually still be sitting at around a mega electron volt. This requires some unconventional assumptions about the interactions of the QCD axion with pions. You have to be in what's called the pion phobic limit of an axion. But putting that complication aside, they studied this sort of parameter space where you're looking at the coupling of the electron here on the vertical axis to the mass of the axion. And they have all this open parameter space where they thought you can have the QCD axion interacting with electrons. But here you're seeing the power of the bounds that I was showing you for these pion decays that are interacting with leptons. They rule out all the parameter space here quite dramatically. People have also studied the possibility of axions mediating the xenon 1-ton excess. Here you're seeing again the coupling on the vertical, the mass on the horizontal, and various different experiments that are being shown here. The best fit for the data was this blue region shown for you here. And our bounds again rule out all this parameter space. The final example that I want to mention is for the atomic key excess. This was an excess in beryllium decays that many of us probably have thought a little bit about in the past, including myself. And here you're seeing the bounds again overlaid on these different parameter spaces. So what I want to highlight here is even for the standard vertex, these new pion decay bounds are really critical in understanding the viability of whether it be the QCD axion or explaining various different anomalies. And with that, I just want to conclude. The kind of big point that we try to understand is what is really the theory of leptophilic axions. And the surprise that I did not expect coming into this project, but I kind of learned as we went along here, is that you really have to distinguish two different cases. One is the possibility that these interactions are commuting with electroweak symmetry, if you wish, or that they preserve electroweak symmetry, and the other is that they are weak violating. And there's strong bounds in these various different cases from charged meson decays, W boson decays, and proton beam dumps. There was a question in the audience. Maybe I'll just say this last few words and then I'll come to that as we wrap up here. Just kind of wanted to make a couple of more general comments even. The surprise here for us was these kind of weak violating ALPs were not discussed in the literature, but they really drive a whole new set of new phenomenology and quite rich phenomenology as I was showing you. And there's probably a lot more opportunities to try to look for them and understand their viability. I think that would be very interesting to look into in more detail. And finally, I want to comment that while weak violating might seem like a bit of an unusual assumption, in fact, every model has weak violation through RG running. So maybe there's some sort of implications that you can try to leverage that in studying all sorts of axions in kind of trying to exploit these weak violating interactions over what we've already done, but focusing on the RG running effects. Okay, thank you.
Excellent. Thank you, Jeff, for that really great talk. And I see we already have one question from Baha. Please go ahead, Baha.
Hi, great talk. Thank you. I have a question about this coupling to neutrinos, the 4-point coupling. As you know, the tritium beta decay experiments are quite sensitive to the neutrino mass because of the kinematics. If you have a coupling like that, that certainly will change the kinematics. So my question is, are there any constraints on that from experiments like Katrin?
Yeah, that's a wonderful question. I don't know the answer. I haven't tried to do that calculation. Yeah, I don't know the answer, and I'd be very curious to know. It's not one of the processes that we studied, so I'm not sure, but it'd be very interesting to see if there's actually a bound from Katrin as well. I definitely agree that there should be a bound. Whether it's competitive with the other bounds, I don't know.
Well, that's different, of course.
Yeah.
That's a different story.
Yeah.
Sure. Thanks.
Yeah, a very interesting question. Thanks.
And now I see a hand from Shashank. Go ahead, please.
Yeah, I have a question regarding the W boson decay. And you said that you can basically look at the W boson decay width essentially and get limits on the axion decay. Now, my question is, how is the W boson decay width measured in the PDG data, where it is coming from? Because from what I understand, you cannot take a bunch of Ws and see them decay the way you can do it with pions. You have to do it in a beam where you can only access high PT events. So there will be a bias towards the two-particle decay. So is it justified to just take the decay width from the PDG and put a limit on the decay? Because when PDG is reporting the decay width, it is not looking at all possible decays. It is looking at a subset of the decays, if my understanding is correct.
Right. So
So
my understanding is the total width is calculated or is measured at through LEP. And there, what happens? You have a lot more control, right? You have an E plus E minus initial state. You can decay to quarks, and there you can see the real Lorentzian of the W boson. And I think that's the measurement that's being used to kind of set this sort of bound. So it's not a sum over different processes that are computed, but instead I believe that they're looking at one particular channel, for example, E plus E minus to Q bar Q, and trying to look at the distribution of the invariant masses to get the width directly at LEP.
okay, thanks.
Yeah, interesting question. Yeah, it's kind of a subtle bound for sure. It's a little bit different than we kind of normally do this sort of process, but there's just no bound other than this that I know about that would make a splash here.
Great. I actually had a question about, I was just curious if you've had success drumming up support for this dedicated search in the W decays.
I haven't tried yet. It's something that I definitely am interested in doing, but I haven't had a chance to talk to anybody that's kind of in these sort of looking for such kind of channels and try to carry that out just yet. So I haven't tried.
Great.
But there is a large Atlas group here. It'd be interesting to try to talk to them and try to understand the prospects. They're kind of doing a little different stuff. They're focused very much on Higgs decays, but it'd be interesting to maybe see if they or somebody else be interested in kind of pursuing this channel.
Do we have any other questions for Jeff? I see Jeff. Go ahead, Jeff Perryman.
Hey, Jeff, thanks for the really, really lovely talk. My question's kind of a variation on Baha's question, but so of course the tritium decays could in principle give you access to this mechanism if it were operative. But I guess more broadly, what's the landscape of nuclear physics searches for this? In particular, I would expect that this should affect like not just neutron lifetime, but neutron decay correlations, other kinds of nuclear decay correlations. And I guess in principle, kind of thinking about it, this would be something that one could imagine might manifest at something like ISODAR, where you have as much as 13 MeV of energy available to produce an MeV scale axion, and then it doesn't have to travel all that far in order to perhaps decay into a detector. I would guess this would be kind of harder to look for at nuclear reactors because it doesn't lend itself well to that particular coincidence signal. But I just wonder if you've thought about because now this is starting to get to the energy range, because the tritium measurement limits you below, what is it, 18 and change keV. But some nuclear processes do start to get you into the 1 to 10 MeV range. And you show these constraints where there were the bounds that you derived, and then E137, and then supernovae constraints, and that pretty much seems like it has the part of that parameter space that you showed on lockdown. But as many pions as we have, we of course have a lot of nuclei as well, and there are a lot of decays that will happen at ISODAR and in principle in nuclear reactors. And so I just wonder if this is something that that you can comment on, or if you've thought about. I appreciate that. That's kind of a meandering question, but
no, it's a very interesting point. I haven't thought about it very much, but I think the point that you were making, which I definitely agree with, which I didn't think about with the tritium case, when that was earlier mentioned, is that there is a kinematic issue. Is that I'm a little worried that above, I mean, to really kind of get into parameter space, which is not extremely small couplings, you really want to be something above, if you wish, kind of 10 mega electron volts, as shown here. Below, you'd have to reach very, very, very tiny couplings to beat out the beam dump experiments. So you'd have to look for relatively high threshold processes in nuclear reactors. And maybe that's possible, but yeah, you're definitely kind of pushing the kind of the possible process you can look for. And Katrin being an example, I'm not sure if they would have enough kinematics to really get in here for that reason, because the tritium threshold is very low.
Okay. Yeah, I mean, I can buy the argument that basically all these other existing searches kind of eat your lunch. But I know if you were an enterprising individual who's interested in trying to come up with all the new physics things that ISODAR could do, for instance, then perhaps this would be an object, but it seems like all the work that's been done has been too good. People worked too hard and were too smart and got a good constraint. So that's good for them, I suppose. But yeah, again, thanks again, Jeff. This is really nice talk.
Yeah, thanks so much. Yeah, it's interesting. It's a good question. I haven't thought about these nuclear decays, and maybe there's some that are very high threshold that'll help you push that regime. I'm not sure.
Last call for questions. Okay, if not,
I have a
let's-
quick-
oh, yes.
I have a quick
please.
question. This kind of digressing in the theory aspects of axions. Is there any reason to suspect that, in theory, axions could couple to like gravitons? And if you had axions that collided, could that result in the production of gravitons that could be searched for using future colliders?
Well, that's an interesting question. I mean, my first thought is that certainly the coupling is going to be there,
Okay.
but it's probably going to be very small. So I can write down a coupling like axion Ritchie, so RR tilde really, and I could try to look for that process. I don't know how much work has really been done to try to search for that.
Right.
Nor where exactly you would start to look for that process. But I would definitely expect that coupling can be there. I mean, why not? You have a photon coupling. Well, why not have a graviton coupling? But I don't know how much has been done in that direction, nor do I know how, like, if there's any sort of kind of maybe less direct bounds that would kind of rule out any prospects of a low scale for that a Ritchie interaction.
Mhm. Right. Okay.
So it's an interesting question, and I don't really know much literature which is focusing on it, but maybe it's worthwhile looking into in more detail.
Okay. Thanks a lot.
All right, let's thank Jeff once again, and I will now stop the recording.